Hello dear students, and welcome back to this series of lectures on biodiversity. In fact, in the last lecture we talked about latitudinal species diversity gradient and what are the factors that influence this diversity gradient. And we talked specifically in the previous lecture about the biotic explanations or biotic hypotheses that explain this diversity gradient. In today's lecture, continuing that debate, we will be specifically talking about abiotic explanations. I told you last time also that the abiotic explanations or hypotheses include number 1, time hypothesis, number 2, climate stability and area hypothesis, number 3, production hypothesis or productivity hypothesis, and number 4, evolutionary speed hypothesis. Let's begin with the evolutionary time hypothesis. You must be knowing that communities diversify with time. When we compare tropics and templates, templates sustain relatively younger communities than tropics because they have recently evolved or recovered from the glaciation and the climatic disruption. Species that could live in temperate areas or temperate regions have not been able to migrate back into the tropics or into the unglaciated species from the unglaciated areas have not been able to go back to the glaciated areas, because let me tell you here, when the last glaciation phase took over the earth, it is said that the glaciation phase did not reach completely to the tropics. Of course, it did cover completely all the temperate areas, but it was not able to reach the tropics. And up to the areas to which it came, it completely vanished all the species and disrupted the evolutionary cycle. Now, I told you that species that could live in temperate regions have not been able to migrate back from unglaciated areas into which the ice age drew them. This is an ecological theory or ecological explanation. And second important explanation is that resident species in temperate areas have not been able to evolve, or they have not yet evolved new forms to exploit vacant niches, what is also sometimes called as evolutionary theory or evolutionary explanation. There is experimental support in favor of this hypothesis. Sanders in 1968 provided evidence in support of this evolutionary time hypothesis by comparing benthic invertebrate communities in glaciated and unglaciated lakes, which of course do exist on almost similar latitudes in the northern hemisphere. They include the Lake Baikal, which existed in the former Soviet Union, and the Great Slave Lake, which exists in Canada. Let me tell you here, it is a very interesting comparison made by Sanders. Since two lakes, which almost in other parameters or other things are almost similar, the only thing in which they vary is that one has been glaciated and another is unglaciated during that phase of glaciation. And in this glaciated lake, only 4 species were recovered in comparison to the unglaciated lake, wherein more than 500 species of these benthic invertebrates were recorded from this. By this, we can get an idea of how huge an influence this glaciation have had in past in disrupting the normal evolutionary cycle in temperate and other areas and not in the tropics where it was not able to come. The second abiotic explanation is the climatic stability and area hypothesis. As students of ecology or plant sciences, you must be knowing that larger areas with climatic similarity and stability do contain and sustain more species because larger areas support bigger populations than smaller areas with relatively fewer rates of extinction, because larger the population is, less are the chances of extinction. And in smaller populations, or what we sometimes also call as fragmented or metapopulations, the chances of species extinction are more. In tropical regions of 2 hemispheres, if you just try to see on the 2 lines of the equator, we have on the northern hemisphere and on the southern hemisphere, the 2 tropical regions are adjacent to each other, and they create together one large area with one similar climate, as compared to the two areas, say temperate areas of the two regions, northern and the southern hemisphere, which are disconnected by this tropical part or tropical ribbon. So this makes this contagious large area, tropical large area possible. As such, facilitates the existence of larger populations, thereby reducing the chances of extinction. This theory is not without criticism. The hypothesis in its first place is unable to account for relatively few species in the vast contagious land masses of Asia. Also, this theory does not explain why in tundras, which are the very large biomes, yet very species poor. That means not only being large is enough, there are some other factors also that do play their role in determining the species diversity. And for that matter, you must be also knowing that the biggest volume of any habitat is the deep sea habitat, isn't it? Yet it has fewer species. So many factors are there which do basically interact and determine the overall species richness in tropics. The next hypothesis is the productivity hypothesis. And this hypothesis proposes that the greater primary production by plants results in greater overall richness of species in a community, because a broader energy base in a pyramid, particularly in an energy pyramid, it permits more species in the pyramid. Now, in fact, the light, temperature, precipitation, and other regimes in tropics lead to high biomass communities, but not necessarily to diverse communities. We say that conditions in tropics are ideal, so we can say that there can be more abundance of species, but not necessarily more number of species. As I told you earlier also, that tropical soils are nutrient poor than the temperate soils, because whatever nutrients we have in soils in the tropical regions, they are immediately recycled and locked up by the living biomass, by the huge diversity of microbes that do exist in the soils. So this productivity hypothesis again does not clearly tell us why tropics are more productive and temperates not, and why do they sustain more species and temperates do not. So the main criticism of this theory is that it fails to explain why some tropical seas have low productivity but high richness. And by contrast, eutrophic lakes, you must be knowing, have high productivity but low richness. And you must be knowing that eutrophication leads to a phenomenon what we call as bloom formation. And in bloom formation, it is just one species that makes best use of the nutrients available and proliferates at the cost of other species, thereby reducing the diversity. And what's very important here is when we talk about productivity hypothesis, we have not to talk about the quantum of nutrients that is available, but also about the variety of nutrients available. If we have more quantities and also more varieties of nutrients available, then of course productivity hypothesis is all set to explain more number of species in a more productive environment. In marine ecosystems, let me tell you here, some of the highest productivity systems which are found in Antarctic oceans, which have only few species. So this is again a criticism of this theory. Then the next very interesting theory is the evolutionary speed hypothesis. We talked earlier about the evolutionary time hypothesis. Communities diversify with time. Here let me tell you that effective evolutionary time promotes high species richness and results from two important things. One is the evolutionary speed. That means at what pace, at what rate, at what speed does evolution take place in a given system. Second is the geological time during which the ecosystems have been existing under more or less uniform or same conditions. Evolutionary speed in turn promotes species richness because of higher temperatures in tropics, as we generally believe. Because higher temperatures are known to foster, number A, shorter generation times, number 2, high mutation rates, and number 3, increased selection which leads to selection of favorable mutants only. Of course, this is a good explanation, but the important criticism of this theory is that while we know that the generation time doubles or it is accelerated by temperatures, there is not sufficient evidence in favor of the second and the third proposition of this hypothesis, that higher temperatures do induce higher mutation rates, and how does this higher temperature increase the selection that leads to the selection of, say, only favorable mutants. These are some of the criticisms of this evolutionary speed hypothesis. When we critically analyze all these hypotheses, be them biotic hypotheses or abiotic hypotheses, we would come to the conclusion that overall the latitudinal species diversity gradient lacks an unambiguous explanation. But it should not surprise us. Why? Because the components are themselves understood incompletely and in a rudimentary way. And the latitudinal diversity gradient intertwines these components with each other, and often they are sometimes opposing also. So the hypotheses which we have discussed in this lecture, both biotic and abiotic, are neither exhaustive in themselves nor mutually exclusive, but they can be combined in a rational way in many permutations and combinations, let me tell you, to arrive at a more logical conclusion and have a common conceptual framework and a single explanation for its overall and easy understanding. Let me tell you here that there are some exceptions to this classical diversity gradient. To begin with, in the lecture, I have told you that the latitudinal species diversity gradient is one of the ecology's oldest, fundamental, and widely recognized patterns of global biodiversity distribution. Yet it is not without exceptions. A number of exceptions do exist regarding the strength and the direction of latitudinal species diversity gradient. In a small proportion of cases, the relationship between species richness and latitude has been found not to be that significant, just not more than 10% significant. And these exceptions primarily do exist, or they are associated with, number A, the narrow latitudinal extent, that is a form of scale dependence. Second, the species with parasitic life histories, they do not adhere to this pattern. And number third, aquatic floras. Aquatic floras do not show such distinct latitudinal diversity gradient as it is exhibited by the terrestrial ecosystems or terrestrial floras. Many of the exceptions to the classical patterns, near about 36%, they have been associated with scale, and they have been found to occur when the gradients in richness was quantified over short latitudinal scales. That means the first important thing that I told you in the introductory remarks of this lecture, that when we talk about the diversity gradient along a latitudinal scale or along any spatial scale, we have to be very specific and precise about the level or scale that we are talking about, because at local scale, at a regional scale, and at a biogeographical scale, the impacts can be different. Well, in conclusion of this lecture, let me tell you that although the patterns of global biodiversity gradient or distribution are relatively well understood or documented, understanding why they exist at all, it comprises an important question for ecologists and biogeographers. It is a kind of an intellectual challenge to come out with an unambiguous explanation for this. However, the most realistic way of understanding the latitudinal richness gradient is that different factors and different processes do act on different scales, while biotic factors such as competition, predation, or species interactions, they do operate more at a local scale. The evolutionary processes act more on a biogeographical scale or a continental scale. And in this lecture, I hope you might have got an understanding and a basic idea of the synthesis of the most promising hypotheses that have been advanced to account for this latitudinal species diversity gradient. Yet, the real challenge now is to develop a unified and empirically testable theory out of these apparently overlapping hypotheses that would provide a sound conceptual framework and basis for understanding and interpreting this latitudinal species diversity gradient. With these remarks, I take leave of you, and till we meet in the next lecture, goodbye.